So here's a property of higher homotopy groups, which is easy to state and is also rather easy to prove. It might be this bit surprising the first time you see it, though. Okay. Fundamental group we see is highly non-abelian. It has very great richness coming from its non-abelian structure. We'll see a little something related later with higher homotopy groups, but they are abelian. Yeah, so this is actually more surprising that you can't compute them very often, because abelian groups can be described very precisely. They're often finitely generated. Okay, so let me just write this as a theorem here. So if n is greater than or equal to 2, f star g is homotopic to g star f. Here it's fixing endpoints, where of course fg are going to be maps from 0, 1 to the n relative to its boundary, and to the pair xx0. The proof is going to be a bunch of pictures which you can make into formulas, but it's better to view them as pictures. So here is f. So f star g is, well, what is it? It is f here and g here. Okay, and the boundary maps to the base point. So instead of black, let me make it purple to emphasize. This is a region that is mapping to the base point. Okay, here I've written equal. It's actually equal up to homotopy. Well, but this is homotopic to the following map. Okay, so let's first draw the rectangle. Let's make f tiny here, g tiny here, and what I'll do is fill up everything else with a base point. So not only is this mapping to the base point, but so is of course this whole square and the outer square as well, but everything in between. This is simply a radial homotopy which is going to map, well, the boundary anyway went to the base point of the cube. It's going to map these things inside. Okay, that's nice. So now f and g have become tiny, and as a result I can move f maybe like this and move g maybe like this to get homotopy between this time g here and f here. Okay, so again the whole thing in between is the base point. It's very similar, so I'll be less. Let me point out what this is. So this is compose with a family of self homeomorphisms, and rel boundary of 0, 1 to the n. Meaning these are homeomorphisms, they fix the boundary, you can even fix the neighborhood of the boundary. Maybe you can push f up and push g down, and you pre-compose with them more precisely. That is, I have a function from 0, 1 to the n. If I apply the same function, but first I have a map from 0, 1 to the n to itself, and it's a rel boundary, it fixes the boundary at all times. And then I get a homotopy. Okay, even fixing boundary is not essential here because the whole boundary moves to base point. You'll still get a valid homotopy, which if you do this. So you just move, catch your finger and move f up, move g down, first by homotopy. So family of homeomorphisms, and when you post-compose you get a homotopy, then you move them across each other and then move them back here. And this is homotopic, undoing the first move, of course, to g and f, undoing the radial homotopy, which is g star f. Okay, so nice and simple. What you see is that these are abelian groups, and as soon as n is greater than or equal to 2. Worth noting that if n equals 1, you don't have the room to move these up. You're using the extra dimension to be able to move them, and the fundamental group is indeed not abelian. Okay, so this is one of the nice things we know about homotopy, surprisingly easy and perhaps a surprising statement as well.